Okay, in this video I want to show you guys different ways of solving the same problem. So for some of the more complicated problems, there's not always one preferred or have to do it this way type of solution pattern, but there's multiple ways to do it. So we're going to take this problem from problem set 1, which was problem 1.26 with the cop car and Jim, and I'm going to show you 3 different ways you can solve this problem or approach it. So the problem is Jim driving his car at 30 meters per second along a highway where the speed limit is 25 meters per second. A highway patrol car observes him pass and quickly reaches a speed of 40 meters per second. At that point, Jim is 200 meters ahead of the patrol car. How far does the patrol car travel before catching Jim? So my 3 different approaches, I'm going to start with what I'm going to call my traditional substitution approach. This is an approach where you have multiple systems or a system of multiple equations, and you connect the 2 equations by some variable that's common, and then use substitution, or you could use elimination or some algebraic means of simplifying it and solving it. So I'm going to zoom in on this one portion so it's easier for you to see. So for traditional substitution, I need to first set up my system of equations. This is the first challenge. So I begin with a picture, and I get a picture of the cop car and Jim. Jim's moving 30 meters per second at a constant speed. The cop car is moving 40 meters per second at a constant speed in the same direction. And at the time of the problem, they're 200 meters apart. So what I'm going to say is, at some point, the cop will catch Jim because he's moving faster, right? So if I let enough time go, he's going to close the gap and he's going to catch him at some point in time. And I don't know when that is, but I know that Jim's going to travel a certain distance, which I call d Jim, till the cop catches him, and I know the cop's going to travel whatever the 200 meters is plus how far Jim travels. So d Jim plus 200 meters. So that's an equality we can use to link the 2 problems together. So let's set up, these are basically my givens. The other thing I know, besides that the distance Jim travels is plus 200 meters is equal to the distance the cop's going to travel, we know that they're going to travel for the same amount of time. So really, I have one time in this problem, which I'm going to call delta t. So then in my guess steps, I'm going to start with my equations. Now I've already solved this through, and so why don't I just show you a bit at a time. I set up a relationship for the speed of the car, which is the distance of the car over the time. I set up a relationship for the speed of Jim, which is the distance Jim travels over a certain amount of time. And what I wanted to do was use the fact that the times will be the same. And I solved this equation for Jim's speed for time, which is the distance of Jim over the speed of Jim, and then substituted that back into the equation for the speed of the car. So I got one equation in terms of the speed of the car, the speed of Jim, and the distance of the car and the Jim travels. So it appears that I have 2 variables, but I can eliminate one because I know that the distance the cop travels, it will be whatever Jim travels plus 200, which I set up here. So once I substitute that in, I have one equation, the speed of the car equals the speed of the Jim times the distance of the cop over the distance of the Jim, which is this, basically taking the denominator and putting it to the numerator. And then when I multiply both sides by dj, which I did here, and then substitute for the distance of the cop, I get this expression, right, equals the distance of the Jim travels times the speed of the cop car. So then I need to solve for the distance. My only unknown is distance of Jim. So I have like terms here, speed of the cop times distance Jim, speed of the cop, or speed of Jim times distance. So I send that to the other side, I subtract it, and then I'm just going to show you the rest of my algebra here. I divide by, I filtered out or factored out dj times sc minus sj, then divided by that to get distance Jim by itself, substituted in at the end with my units, and if I do that correctly, if you want to pause it and try to write this down and follow my steps, what I would see is the distance Jim travels is 600 meters till him and the cop are in the same place. So if I add that to the 200 meters that separated them at the beginning, I would get that the distance the cop car traveled was 800 meters before catching Jim. So for some of you that are strong in algebra, this is a way that can always work. You know, using substitution, setting up a system of equations, and using equalities or things that link the two equations to eliminate variables. It's a pretty traditional physics approach. Now I'm going to show you another way, and that is what I'm going to call the graphical approach. So let's start here. Let's get this zoomed in. I'm going to graph the motion of Jim and the cop on a position time graph. So if you take a look at the position time graph, you'll notice that at time 0, I have denoted that the time that the speed is the cop is moving 40 meters per second and Jim is moving 30 meters per second. So the distance between them is what I see is my delta x, or distance between x cop, which is 0, and x Jim initial, which is 200. So they start 200 meters apart. And then notice that the cop car's slope is steeper. His slope is 40 meters per second. Jim's is 30. Okay, and what I know is if I plot these two as a linear graph, I can come up with a linear expression. I can figure out where they intersect. And wherever they intersect at that time, right, that's going to be the position they're at. From there, I can figure out how far either of the cars traveled. So at time 0, it's just how I set it up. You know, position of Jim is 200, position of the cop is 0, and then I know that the slope of each is their velocity. Jim's is 30, the cop's is 40, so I use the slope to draw the line, so I plotted some points for each. And then the equality that I use is essentially based upon some equations I came up with. Because these are both linear, my y variable is position. The position of Jim equals his slope, which is the velocity, times the x variable. This is all y equals mx plus b format. So I didn't write that down. Maybe I can write that down so that you're aware. So this is y equals mx plus b, slope, intercept, where y is position, m is the slope, which is the velocity, x variable is time, and then my y-intercept is 200 for Jim. And for the cop, there is no y-intercept, it's 0. So I have these two equations. Position of the cop is its slope, 40 times the x variable t. So if I look at this, if I were to set these equal to each other, right? So wherever these two functions equal each other, I'm going to have an intersection. So I take the position of the Jim, set it equal to the position of the cop, and then I solve for t. That's my variable that's common. So at whatever time I solve for here, that's the time at which these two lines will be at the same point, which is where they meet. So I do that. I do work out a little algebra. Now notice this algebra is a little bit easier than what we did with the substitution. And so sometimes using a graphical approach can give you a little bit of an easier bit of math to do if you can visualize this well. So I find that if I simplify this, I get time of 20 seconds. So at time 20 seconds, the two lines intersect. And so then I figure out, well, at time 20 seconds, what position am I at? And if I use the slope of each, after 20 seconds has gone by, the cop is moving 40 meters per second. So if I calculate that, the position change of the cop is 800 meters. The other thing I could do is just plot the lines specifically and plot it well, and actually use the rise over run, and just see where they intersect and figure out what position that's at without using any algebra at all. So that's another way you could approach it. It gets harder with constant acceleration because you have nonlinear graphs, which are a little harder to plot. But for linear, constant speed relationships, this is definitely a good approach. Now the last one is what I'm calling the relative velocity approach. So the relative velocity approach essentially takes a different way of looking at the problem. One of the things we're going to talk about a lot in this class as we get into more complicated problems are this idea that motion is relative, this idea that from one observer's point of view, everything else moves relative to them. So if I'm moving on a train, relative to me, it looks like the ground's moving, right? But relative to the ground, it looks like the train's moving. So we can use this relative approach as a way of solving problems like this. So the way I would do that is by trying to look at this problem from the viewpoint or the vantage point of one of the cars. So we'll take the same setup, right? The two cars are moving at different speeds in the same direction at a distance of 200 meters apart. And what I want to say is, let's look at how the cop car is moving relative to Joe. So if I'm Joe and I'm driving in my car, right, I'm moving 30 meters per second relative to the ground. The cop is moving 40 meters per second relative to the ground. But if I'm in the car, it appears as if the cop is moving at me at a speed of 10 meters per second, or whatever the difference is between those two speeds relative to the ground. So you can take this problem and solve it from the reference point of Joe and say, all right, how long will it take for the cop car to meet me in my reference frame, which makes it a lot simpler. So if I say the distance between me and the cop is 200, and the cop relative to my position is moving at a speed of 10 meters per second, it's going to take 20 seconds for the cop to then reach the same point as where I'm at. Okay, this is the same result we got from the graph over here, right, where it was 20 seconds where the two lines intersected. So, relative to the ground though, because the question is asking me how far does the patrol car travel before catching Jim. That's a question relative to the ground. So I have to go back then and use the speed of the car relative to the ground, which is 40 meters per second, and take the 20 seconds it takes to catch up, and voila, I get the same change of position of 800 meters. So I think this is an important video for a lot of you who might have a little bit of trouble always picturing problems from a traditional longhand substitution point of view. And I wanted to show you that there are other ways you can be creative in approaching problem solving, and encourage you to think about a problem from the perspective of how can you set up a relationship, how can you set up a system to solve for the answers that you're looking for. And hopefully this helps out.